Welcome everybody to another Stealthness coding session. Today I'm going to look at test-driven development and how it can be used to create a algorithm solution to a known problem, and the known problem we're going to use it on is the Fibonacci numbers. Fibonacci numbers have been known for a long time. They're a well-studied mathematical sequence, and today we're going to use them to show how that test-driven development can be used to actually create a solution for the problem. Now, for those who are unfamiliar with Fibonacci numbers, a Fibonacci number is the sum of the preceding two Fibonacci numbers. And the first of the sequence, we set also the first Fibonacci number is initialized as 1, and the second Fibonacci number is also initialized as 2. Therefore, the Fibonacci number 3 would be the sum of Fibonacci numbers 1 and 2, so that's 1 plus 1, that's equal to 2. And this Fibonacci sequence would then go on 1, 1, 2, 3, 5, and so on. So without further ado, I'm going to start. I've already got a class here called Fibonacci, and I'm going to create a static method to get a Fibonacci number. So it's going to be static, it's going to return an integer, and we're going to call it getFib, and it will take in a integer which will be the Fibonacci number that we're interested in returning. Because it has to return an integer, we need to actually return something. In this case, I'm going to return -1, just so that I get a bare bones method that I can then just compile. So to generate a test, we can use the IDE and we can create a test. And here it is. So we're going to generate it for the getInt. We're going to have the class name. We're going to use JUnit5, and it should automatically put it into the test folder, and there we have our test. So the first test I'm going to do is I'm going to just basically set that test that fib1 return fib1 returns 1. So we're starting off with the very basic, which is we expect that when we run the test, that if we put in for getFib1, we should get the value of 1 return. Now I'll use the ID to add on the thing, which it has done. Okay, annotations are not allowed. That's because I too sure why that's going. Well, that's because I haven't actually added that part. Okay, and then we're going to use the assert equals, and we're going to have our expected result, which is 1, and our actual result, which is we're going to call Fibonacci, and then we're going to call it getFib, and we're going to call it on 1, and basically we expect that when passed to return us 1. Okay, and then we just need to add that method, and there we go. So now we've got a test that we can run, and remember, whenever we create a test, we should always run the test to make sure that it fails. There's nothing worse than having a test that you created and it passes, which tends to suggest that either you are blind lucky in the way the code runs, or there is something else that's more fundamentally wrong. And as we can see, our expected result of 1 is incorrect because our actual result was -1. And if we go back to our Fibonacci's class, we can actually kind of see this, and I'm going to actually split this vertically so that we can see later. We'll just make it a little bit larger for those with the hard of eyesight. And we can see that when we get fib, it just returns -1 regardless of whatever the number is. So let's put in the first one. So if brackets number is equal to 1, then we shall return 1. So it's the simplest solution that we're getting here, and that's it. So when we rerun the tests, we now see that we've actually passed our test. So we're going to move on to the testing for the next thing. So the next simplest thing that we can test is that we know that when Fibonacci number is 2, it is also returns 1. So let's test that. Okay. So at test void test that fib2 returns 1. And in this case I can pretty much, I'll copy that, and then we just need to change that for when the number 2 is in there. So we've created our tests, so let's run our test. And as we can see, it passes our first test, which is good, but our second test is wrong because it expects 1 but is actually returning -1. So we should put another condition, else if number equals 2, we shall return 1. Okay, we save that all up and we shall run our tests. And now we can see that we've passed all our tests. Now one of the things about test-driven development is it's a cycle. So we write a new test, we test that new test to make sure it fails, we then write the code so that we can then pass that test, we run the test to make sure it passes and all the previous tests, and then there's also a fifth thing that we need to do, which is called refactoring. This is where we look over our code and we see in our solution, can we make it more elegant, simpler, easier to understand? And in this case I look at the Fibonacci and I realize that we're doing a test for number equals 1 and we're doing another test for number equals 2, and they're both returning the same thing. So I'm actually going to remove this part and I'm going to change the if and say if number is equal to 1 or number is equal to 2, then we return 1. So I run that and we should hopefully get a passing test. And there we have a pass. They both pass. So we've refactored the code to make it simpler and more elegant. So now we need to move on to the next one. So we've tested for when the Fibonacci number 1, we tested for Fibonacci number 2, and so it will not surprise you when we test for the next number. Void test that fib 3 returns 2. So the third Fibonacci number shall return the sum of the previous two, which is 1 and 1, and that makes 2. So that's what we're expecting. So again, I'm going to copy this to save myself typing it, and then just change the new things. So when we put in the third Fibonacci number, we expect to get the result of 2. So we run that to make sure it's failing. And as we can see, our expected result was 2, but we actually received -1. So we'll go to our code and we look. So we can put in here, else if number equal to 3, return 2, and we shall run that. And there we see we have our pass. So now I'm going to also do some refactoring. And here I'm looking at, we have if number equals 1, number equals 2, return 1, else if return 2, and if none of that works, then we're going to return 1. And I'm thinking to myself, a switch statement would be a little bit more readable here. So I'm going to use a switch statement. So we're going to switch on the number. Okay, and I've got, so far, we've got the case of 1. We've got the case of 2. We've got the case of 3. And we've got the default case. Okay. So in the case of 1 and 2, we know that that's returned 1, so I can put that there. And we know in the case of 3, it's going to return 2. And we know that in the default case, if it's none of those, we're going to return -1. And we no longer need that. So here we can see it's a little bit more readable. And so if we run that, we should hope to make sure that it passes all our tests, as we've just changed the code, but we're not actually added any new tests. And there we can see that it has indeed running there. Now we move on to the next one. So I'm actually going to copy that whole function, and we're going to move on to the case of Fibonacci 4. So in the case of Fibonacci 4, it's going to return the previous 2, which is 1 and 2. That makes 3. So we expect 3 when we put in the number 4. So after we've added our new test now fails. So we have to add in the king, and so that's a new case. That's the case of 4, and that returns a value of 3. So we shall now recompile our tests and run them again. And we can see that pass. So now I look to see at the code. Now I can see that this would just continue if I was to have case 5. Then I'd have to hard code in the result there. I'd then have case 6, and so on and so on. So there must be a better way to do all these, because we don't want to continue to run an enormous case run. And what we need to realize is that from the numbers from 3 onwards, we're actually going to use the actual Fibonacci algorithm itself, in the sense that at all times the numbers are the sum of the previous 2. So what I'm going to do here is I'm going to make a change. Now unfortunately I can't put for all numbers 3 or greater, unfortunately. But what I can do is I could put a conditional at the beginning. So if number is equal or greater than 3, we're then going to return the sum of the previous two, and here we're going to use recursion. So we're going to return the number minus 1 plus the number minus 2. So I haven't said anything about when the number is 1, 2 or less than 1 or 2. I've only said only if the number is greater than 3 am I going to actually use the recursion to work out the values. So I'm going to run that. And then they all pass. So the next thing I'm going to test is I'm going to test for what happens when I put the value 0 in. Well, for Fibonacci numbers, the value of 0 is not actually defined. Now, there is an argument that the value of Fibonacci 0 could be 0, but in the classical definition of Fibonacci, it's not actually valid. So we're going to test that fib 0 throws illegal argument exception. Now for this we're actually going to use a slightly different way of doing this. We're going to use a different assert. We're going to assert. You can even actually see that it comes actually as one of our choices. We're going to use assert throws. So we put in the actual type of assert, that exception that we wish to catch. So in this case it's going to be an illegal argument exception dot class, because we actually want to actually work out what it is. And then from here we're going to then use a lambda expression to run a piece of code that we're hoping will cause an exception. And in this case, it's going to be, if we call Fibonacci, to click on the autocomplete, Fibonacci, get in, and if we run it on 0. So we're going to run that. And there we can see that we didn't actually get an actual illegal throw. Nothing was thrown. And the reason nothing was thrown is because in our logic, when we get to the case of 0, it actually just returns minus 1. So I'm going to actually add the case of 0. And here I'm going to add the throw clause. Throw new illegal argument exception. And there we have that we've passed. But that's not the only time that we're going to get an illegal exception. We're also going to get a legal exception if we use any test thing. If we use any number that's actually less than 0. So I'm going to actually copy this code. So I'm altering that is less than 0. So here I'm then going to put in the value of -1. So I'm going to run that. And again, it's a new test. We should expect that test to fail, which it so does. So now I look on this. Well, and then I realized that, well, I didn't really need this actual thing. I could have put that through on the default here. So we now know that if the number is greater than 3, we run this code. If it's case 1 or 2, then we just return 1. And if it's 0 or 1 or less than, or 0 or -1 or less than that, we know that it's going to throw the illegal argument exception. So we shall well run that. And there we have it here. So now I'm going to test it for a large number. Test. Void. Test. Fib. With a large number. So for this, I'm going to find a large number. While my browser is loading up, I'm going to ask for the 40th Fibonacci number. And here we have the 40th Fibonacci number. So I'm going to copy that. A moment. So the 40th Fibonacci number is that. So I'm going to copy this bit of code. Control-V. And actually, to make it a bit more readable, I'm even going to create a local variable. I'm going to call it expected, and that's going to be equal to 102.334.155. So it's going to be the 40th number, and my expectation is the expected value that I've just created. Okay, so I'm going to run that. Now in this case, while I've created a new test, I am expecting this one to pass. But I'm setting this up because I actually want to set up the next thing that we're going to test. And the next thing I'm going to test is, I'm going to test that whether our calculation can actually make the calculation in a reasonable amount of time. So I'm now going to create a new test. Void, I'm going to test that fib large value count. I'm going to calculate it in a tolerance time. Well, actually, I'm going to rename that. Large number does not time out. So that's the assertion what we're going to test. And again, we're actually going to use another type of assertion. In this case, it's going to be called Assertion Timeout. Okay. And here we're going to put a duration. I'm going to put the duration in terms of seconds. And then I'm going to add a tolerance. I'm going to use a tolerance as a constant, because we should never really have magic numbers where possible. So there, I'm going to create the constant field tolerance, and I'm going to set my tolerance to 2. So I expect this value to be worked out. Now you may need to change your tolerance according to your system. I'm using a virtual machine, so I can already see from here how long this is. So I'm actually setting my tolerance to make sure that this does fail. Obviously, a tolerance when testing a system which you're designing, your tolerance will be dependent upon the requirements of what your system or your designers or the person that's paying for whatever it is would like. They will usually be in the system requirements. So here I'm now going to get the Fibonacci, get the 40th Fibonacci. Get Fib. So I'm going to get the 40th. That's again going to be a lambda method, which I'm going to do there. Another thing that I can also do on this is I can do the lambda method in this form, or I can also do it in that form. It depends on how readability you want. So we're going to run that. And there we can see that it's timed out. And there's quite a few things here. So the way that we're going to get to solve this is we're going to look at our Fibonacci. We're going to use a thing called memorization. So at the moment, currently, whenever we're calling it getFib, we're basically creating 2 getFibs, and each of those is going to call 2 getFibs till eventually it gets down to the case when there's 1 or 2. So what I'm going to basically do on this is I'm going to create a memorization. Now initially I'm going to start with the memorization of what we already know, which is the case of when 1 and 2. So I will create a private int array, and that's going to be equal to a new int array, and we're going to have it initialize initially to our initial values, which is 1 and 1. Because we know that already. So we're going to call this memory. And this needs to be static. Okay, and I've put that actually in the wrong place. That should be there. So that's a class field there. Now because I've created this, I'm actually going to now do some quick changes around here. So the first one is I'm also going to move out the case of when the illegal argument, because if we actually have an illegal argument, I want that first and foremost to say, right, no, this is not going to work, let's start again. So we're going to assume that our number must be greater than 0. So we're going to change that. If our number is equal, actually we're going to just slightly change that. So if our number is equal or less than to 0, make it a bit more readable that way, we're going to throw this. now I don't actually going to need this, because what I'm going to just say here is, so put this extra, we're going to return mem. So what I'm got here is a couple of things. First, if the number is equal or less than 0, throw a new illegal argument, because we know that we already know that that shouldn't work. If the number is equal or greater than 3, then we're going to get fib. And if the number is actually either 1 or 2, well, we know that because we've already created the class field here that already has those fields, we're just going to call that. And remembering, of course, that because our numbers of Fibonacci sequence start from 1, 2, 3, 4, and because computer arrays start from 0, 1, 2, we have to just take off 1 to get the correct index position. So I'm going to run that, and hopefully we're still not going to pass our large Fibonacci, but we do want to make sure that all our previous tests are working. There we can see. They're all working, but the one that we're working on at the moment. So now we're going to have a look at this part. So here we've looked at whether our number is 3. Well, actually what we first want to do is we want to actually look at to see, say this. So if our memory dot length is less than the number, then we know that we need a larger array. So we're going to create a new array. So memory will equal a new array that will be of length number. Now, because it's a primitive integer array, all of those values will be set at 0 by default. But we do know that we want the first two to be equal to 1. So we just need to change that. So now I have a choice. If I know that my memory is I know that if my memory, by this stage, I will have a memory that's large enough. So the question now becomes of whether that actual array now becomes the question of, if it's equal to 0, then I don't actually have that value, and so I need to get that value. And here I then will then add to the number -1 the value of getting the fib number of 2 and the vid number 2. And when it goes through again, it will do the same thing. In this stage, it won't actually execute that code because we've already expanded it to the length of what we need, but it will find that these ones are also 0, and it will go down until it eventually finds when there's memory 1 and memory 0, and so it will then add. And as it goes back through the stack, and it will only do this once, it will then add all the values along this list, so that when it goes and calls it through again, it already knows now that it already has all the numbers from up to our number. And this is going to show you that when we run this, it will then see a dramatic change in the time it takes to compile and run the test. And there we have it. The large number has actually passed the test. And in a moment, I'm going to demonstrate on a whiteboard exactly what's going on in the memory and why this particularly works. Now, there is an alternative version of the solution to the Get Fibonacci, and you could do this via a simple iterative loop, which is very smart and efficient. But sometimes in programming, we often use recursion because it requires us to write less code and is more easier to read. But these are the things that you have to find out through practice and through learning about when and where to use recursive algorithms or iterative algorithms. In a lot of cases, if an algorithm is recursive and actually is what's known as tail recursive, the Java compiler will actually convert it into an iterative solution via the bytecode. There's particular rules that you can learn as you develop coding skills that you'll learn when and where this particularly happens. The reason it doesn't happen in this particular solution is because we're adding two get fibs together on each thing, and because each of those will generate a further two, we can't unfortunately use tail recursion. Okay, now I'm going to explain a little bit more about what's happening in the memory on when we call these Fibonacci. So I'm going to go through now a small demonstration of the idea between of what's going on in terms of the memory for the recursive solution for Fibonacci numbers. Now, on a Java virtual machine, the program sorts out its memory into two parts. One is called the stack, and one is called the heap. And when we run programs in general, our programs will be placed in order on the stack, and any associated objects details may be somewhere contained within the heap, and some of these objects may also link onto other objects, etc. And whenever a function is called, a new function or method body will be placed on the stack, and until that's completed and done, so that will then obviously maybe link to the same memory, but if that calls another object, it might put another object onto the stack. And as the methods are completed, the results are passed back down and they are cleared from the stack. So again, as they are completed, they're passed down and put on the stack, and once the program is complete, it's put on the stack, and every so often a garbage collector will come along, and if it sees any unattached memory locations, it removes them from the heap. So that's a rough idea of what's going on in the Java virtual memory. Now, we're not going to be concerned so much with the heap for this example. We're concerned with the stack. So when we call we decide to call our first method get Fibonacci number, say 5, or let's just say we wanted to call Fibonacci n, we're going to put a method onto the stack, and we know that that method is then going to call at least two other methods, and that will call fib n-1 and also fib n-2. And these two methods will also create two more methods. This one also will create two more methods, and in fact they will keep going until eventually they will reach either fib0 or fib1 or fib2, which we know the results. We actually know the results because they're our initial ones. So fib-1 we'll call fib-2 here, and fib n minus 3 there, and similarly and so forth. And as of course it eventually gets, and the stack will grow and grow and grow. And I'm going to show you this in another way that will make it appreciative of how this stack actually grows. So I'm going to rub this out for the moment. So I'm going to start in this direction. So if we have, and I'm going to just, if we have fib n, it will create at least 2 calls. Fib n minus 1 and fib n minus 2. And that's going to create at least 2 calls. I'm going to just write what it's actually going to call, n minus 2. N minus 3. N minus 3. N minus 4. And these in turn will make 2 calls. These in turn will make 2 calls. And as you can see, I'm already starting to run out of space. And again, they'll make 2 calls. So you can see even after the fifth rank, we are making a lot of calls, and all of these are going to have to be put on the stack, and they're all going to have to work out. And once they worked out their value, you're going to have to pass it down. And this is essentially why when we calculate the Fibonacci of the 40th number, it took a whole 2 seconds for it to calculate, because it had to generate a load of method calls onto the stack and thing. So what does our memory thing do? Well, essentially our memory thing does a very clever thing. I'm going to rub this out. It starts with 2 values, 1 and 1. And then if we make a call, Fibonacci n, it first has a look up here. It says, am I equal or greater than? So if n is greater than 2, we're then going to have to create ourselves a new array. We'll have the values of 1 in there. Then because we're going to create them as integer, and then it will create an n level array. There'll all be zeros from there, and there'll be n of these. And then when we actually calculate it, we're then going to start calculating the values. So it then tries to calculate fn minus 1 plus fn minus 2. Now when it calculates, first looks at fn minus 1, it realizes that it's still 0 there. So it's going to look back and it's going to go back. Now it will create these 2, but for the moment we haven't even actually come to this, because we're still trying to calculate this part. So we're still trying to calculate this part. This part may be put onto the thing, but we're not going to calculate anything in there until this one's correct. So it will then look at fn minus 2. Again, it will put on fn minus 3 there, ready to calculate it too, but it won't actually go any further. It's just going to look at this one for the moment, and essentially it will go all the way down till eventually it will hit Fibonacci 2, and then it will know that value, and then it can add the value there, and so forth. It will then work out the value for Fibonacci 3. It will then work out the value for Fibonacci 4, and it will start going up and returning all these methods. until eventually it fills out that one, all the way up to Fn. But now, this whole bar is now complete. All the values are now in here. So when we come to calculate these values, all these values and any subsequent ones that they generate, it doesn't need to actually go recalculate them anymore. It will just take the values from the array that we have. So in essence, what we effectively have we've turned our recursive algorithm into essentially an iterative solution. And that's how we solve the way of speeding it up. Thank you for watching my video. If you've got any questions, feel free to put them into the questions below. I will attempt to answer them as much as possible, and I hope you enjoyed my video.